Module 5, Lecture A, Data Analysis. By the end of this lecture, you will be able to import simple process datasets from text files using built-in Python tools, compute descriptive statistics for chemical engineering measurements, and interpret data summaries to support engineering conclusions. Importing process data. CSV file reading. CSV files are a lightweight way to store simple data and work with many tools. In chemical engineering, they can hold measurements such as heat exchanger observations, with rows for observations and columns for variables. Reading a CSV in Python means turning the raw rows and fields into usable data types, and built-in tools help beginners inspect and interpret the file before analysis. A CSV file is a plain text file where each line is a record and commas separate the fields. When importing one, identify the header row so column names are not treated as data. Also, convert values from text into the correct data types, such as numbers, before analysis. When importing CSV files, first check for issues such as blank lines, extra spaces, missing values, and inconsistent formatting. Use Python's built-in tools to confirm that rows and columns are separated correctly and that the data is usable. This careful checking matters because every later analysis depends on the reliability of the dataset. Python code, CSV file reading. Safely read, process data from CSV files, convert text-based measurements into numeric values, and summarize the results so they can be interpreted for engineering decisions. We import the CSV module to read and write CSV files, a common format for sharing data. We also import path from pathlib to work with file locations in a clear, cross-platform way. A string is created to hold a small CSV-style dataset for process measurements. It includes a header and rows for different time points, with values such as temperature, flow rate, and pressure. This lets us practice reading CSV data without needing an actual file. We create a new CSV file by defining its path with the pathlib path class, which works consistently across operating systems. Then we use the write text method to save the CSV data as a UTF-8 encoded string. This produces a small local CSV file that can be read and processed later. The process begins by preparing a place to store valid, complete data entries and a counter for rows skipped because the flow measurement is missing. This setup makes it easier to clean and track the data while reading the CSV file. The code opens the CSV file for reading with UTF-8 text handling, then creates a dictionary-based CSV reader. This lets each row be read as a dictionary, so values can be accessed by their column names. This makes the CSV data easier and more efficient to process. The code reads each CSV row and checks whether the flow liters per minute field is blank after removing extra white space. If it is missing, the code increases a missing value count and skips that row. This keeps later analysis limited to rows with valid flow data. The CSV rows are cleaned by creating a dictionary for each measurement and adding it to the cleaned rows list. The time value is converted to an integer, while the temperature, flow rate, and pressure values are converted to floating point numbers. This makes the data consistent and ready for analysis. First, we check whether any clean rows were imported. If none were found, the process raises a value error to signal that no usable data was processed. This safeguard helps protect data integrity and prevents later calculations from running on invalid or missing data. The clean data rows are separated into 3 collections: inlet temperatures, outlet temperatures, and pressure values. Each collection contains the successfully read and converted data for that measurement, making it ready for later analysis, such as computing averages and other statistics. Calculate the average inlet temperature, outlet temperature, and pressure by adding the values in each group and dividing by how many values there are. These mean values summarize the typical operating conditions of the process. The analysis calculates the cooling drop by comparing the average inlet and outlet temperatures, showing how much the process reduces temperature. It also reports how many complete rows were imported and how many were skipped because flow data was missing. Finally, it summarizes the key operating results: average inlet temperature, average outlet temperature, average cooling drop, and average pressure drop across the system. The script summarizes heat exchanger data from a CSV file by reading temperature, flow rate, and pressure values as numbers. It skips rows with missing flow data and counts how many were excluded. From the complete rows, it reports the average inlet and outlet temperatures, average pressure, and average cooling drop, giving a concise view of cooling performance and pressure conditions. Reading text files. Reading text files is an important skill in data analysis because measurement data, such as temperature or pressure, is often stored as plain text. These files are easy to open and can be read directly with Python's built-in tools. Before analyzing the data, it is important to understand the file structure, since the computer processes it line by line. Before importing a text file, quickly inspect its structure. Check where the actual data begins, whether values appear on separate lines or together, and what separates them, such as spaces or commas. Real data may include labels, introductory text, or uneven spacing, so reviewing the format first helps prevent mixing up numbers and labels and avoids errors later. Python's built-in file handling lets you import data by reading a file as lines of text and converting those values into usable numbers. This conversion is necessary for calculations such as averaging or plotting. It also requires engineering judgment to confirm the data has the expected variables and units, and to notice possible anomalies. Careful file reading supports reliable analysis and sound conclusions about performance and safety. Python code, reading text files. This script reads a small process text file to demonstrate how to inspect lines and convert values. It shows how built-in tools can make data importing straightforward and transparent. We create a string that simulates a small text file of reactor temperature data. It includes a header with the reactor name and Celsius units, followed by column labels for time in minutes and temperature readings. Each later line gives 1 minute and its matching temperature, letting us practice file-style data reading without using an external file. The script opens a reactor temperature text file in write mode, creating it if needed, or clearing any existing contents. A context manager handles the file safely, making sure it closes when the writing is done, even if an error occurs. It then writes the prepared text data into the file, creating a sample temperature log that can be read and processed later. First, create 2 empty lists to store the data read from the text file. One list will hold the time values, and the other will hold the matching temperature readings, making the data easier to organize and use later. The file named reactor temperatures is opened in read mode, so its contents can be accessed without being changed. Its lines are then read into a list, with each line stored as a separate string in the original order. This makes the data easier to process later, such as skipping headers or converting values. The code skips the header lines, then cleans and processes each remaining line of data. For each non-empty line, it separates the minute and temperature values, converts them into numbers, and stores them in their matching lists. This prepares the text data for later numerical analysis. To summarize temperature data, calculate the average to show the overall trend. Then identify the lowest and highest recorded values using the minimum and maximum functions. Together, these measures give a quick view of how temperatures vary during the recorded period. The output gives a quick overview of the temperature data by showing how many records were imported, the first recorded minute and temperature, the average temperature rounded for readability, and the minimum and maximum values. These checks summarize the size, starting point, typical value, and range of the data. The final conclusion is that the reactor temperature rose steadily during the recorded period. This script shows how to read and analyze temperature data from a text file. It creates a reactor log, skips the header information, extracts the time and temperature values, and converts them into usable numbers. It then calculates the average, minimum, and maximum temperatures and prints a short summary of the records. The results show that the reactor temperature steadily increases over the logged period. Naming data columns. When importing process data from a text file, clear column names are essential for understanding what each measurement represents. Vague or missing headings can make chemical engineering data difficult to interpret, and even common labels like temperature or pressure may be ambiguous without context. Using specific, descriptive names reduces confusion and helps ensure the data is ready for reliable analysis. Use clear, consistent names for data columns so analysis is easier and less error-prone. A column name should identify the measured quantity and, when useful, its location or process unit, such as feed flow rate or reactor temperature. Avoid using different names for the same measurement because inconsistent labels can make combined engineering data harder to trace and interpret. Column names should be readable while still preserving essential context, especially units and measurement conventions. If units are not documented elsewhere, it becomes hard to interpret data correctly, such as knowing how temperature or concentration was measured. Clear names or naming conventions help teams connect columns to their meaning, making statistics reliable and supporting sound engineering decisions. Python code, naming data columns. Use clear column names to make imported data easier to understand. Chemical measurements should include enough context and the correct units, and built-in tools can help rename text columns when needed. First, we import the CSV module to read and write structured CSV data. We also import string IO from the input-output module, which lets a string behave like a file. This is useful for testing or working with data already in memory without creating a real file on disk. We simulate a small process data file using an in-memory text string. It includes a header and rows of comma-separated measurements for time, temperature, pressure, and concentration, with each row on a new line. This lets us test file-like data handling without creating an actual file on disk. We use the CSV reader from the CSV module to treat raw text as structured CSV data. First, the header line is read to capture the original column names. The remaining lines are then stored as data rows, ready for later transformation and analysis. The columns are being renamed with clearer, engineering-focused labels that describe both the measurement and its units. These names make it easier to understand the data at a glance, such as time in minutes, reactor temperature in Kelvin, absolute pressure in bar, and product concentration in moles per liter. This improves clarity and reduces ambiguity for anyone using the dataset. Before renaming columns, the code verifies that the number of existing names matches the number of replacement names. This ensures every column has a proper new name and prevents mismatches. If the counts differ, it raises an error, helping protect data integrity and avoid problems during renaming. This step converts each row of data into a dictionary with clearer column names. It pairs each new label with the matching value in the row, then stores those pairs as key value entries. The result is a more readable structure where each value is tied to a meaningful description. The code extracts reactor temperature and pressure values from each record and converts them into floating point numbers. This creates numeric lists that can be used reliably for later calculations and analysis. Basic descriptive statistics summarize the data by finding the mean temperature and the maximum pressure. The mean temperature is calculated by averaging all temperature values in Kelvin, while the maximum pressure is the highest pressure value in bar. This process reviews the dataset by comparing the original column names with clearer, improved names, then shows the first record using the updated structure. It also summarizes key measurements by reporting the average reactor temperature in Kelvin and the maximum absolute pressure in bars, both rounded to 2 decimal places. This script shows how clearer column names make data easier to understand and analyze. It replaces raw labels for time, temperature, pressure, and concentration with descriptive names, checks that the new names match the data structure, and rebuilds each row using those names. It then converts temperature and pressure to numbers, calculates the average reactor temperature and maximum pressure, and prints a short summary to demonstrate the value of clear data labeling. Descriptive statistics, mean measurements. The mean is an important statistic in chemical engineering because it gives one representative value for a set of measurements. It helps summarize fluctuating process variables, such as temperature or flow rate, by estimating their typical operating level. Engineers can compare this average with design targets or past data to judge whether a process is performing as expected. In chemical engineering data analysis, the mean is useful when a process is stable and measurements cluster around a central value. Averaging repeated measurements can reduce random error and give a more reliable estimate. However, extreme outliers can distort the mean, so it should be treated as a starting point for analysis rather than the only way to describe the data. Mean values help engineers turn raw measurements into a simple indicator of process performance, such as equipment effectiveness, product quality, environmental treatment, or energy use. They are easy to communicate, but they can hide variation, unusual readings, or real process changes. For that reason, engineers should always consider how the data was collected and whether any values suggest errors or important shifts. Python code, mean measurements. This example uses repeated reactor measurements to estimate typical process behavior with the mean. It also shows that extreme readings can strongly influence engineering conclusions. This means the code does not require any extra packages to run. It uses only Python's built-in features, so you only need Python installed to execute it. We store 6 reactor temperature readings in degrees Celsius so they can be analyzed. These measurements help summarize typical reactor behavior, such as by calculating the mean, which supports understanding process conditions and making engineering decisions. First, check that the temperature list is not empty by confirming it has more than 0 entries. If it does, the data is valid for further calculations, such as finding the mean. This prevents calculations from being performed on an empty dataset. To find the mean temperature, add all the recorded temperature readings, then divide by the total number of readings. The result is the average temperature, a single value that summarizes the reactor's typical temperature over the recorded period. The engineering target temperature is set to 80 degrees Celsius. This value provides a benchmark for comparing the reactor's mean measured temperature and judging whether the process is operating near the desired conditions. We compare the mean temperature with the target by subtracting the target from the mean. This difference shows how far the average measurement is from the desired value, helping indicate whether the process is on track or may need adjustment. An unusual temperature reading of 86.5 is added to the existing measurements. This creates an outlier, helping show how one extreme value can influence the analysis, especially the mean temperature. To find the new mean temperature after an unusual spike, add all the readings together, including the spike, and divide by the total number of readings. The result is the updated average, showing how the spike affects the overall mean. The code reports how many temperature readings were originally recorded by checking the length of the temperature list. This gives a quick summary of the dataset size before any extra data, such as a spike, is added. This line reports the average temperature after removing unusual spikes, giving a clearer sense of typical operating conditions. The value is rounded to 2 decimal places and shown in degrees Celsius for readability. This line shows how far the calculated mean temperature is from the target temperature. It rounds the difference to 2 decimal places and displays the result in degrees Celsius for a clear, concise comparison. We calculate and print the mean temperature while including the unusual spike. This average is rounded to 2 decimal places and shown in degrees Celsius, helping illustrate how the spike changes the overall temperature value. The analysis shows that an unusual sensor spike raises the calculated mean temperature. This demonstrates how outliers can distort statistical measures and influence engineering assessments. The code first checks that the temperature data is not empty before calculating the mean. If measurements are available, it confirms the data is valid for this calculation. This helps prevent errors that would occur when trying to compute a mean with no data. This script calculates the average reactor temperature after first confirming the measurement set is not empty. It compares the average with a target temperature and reports the difference. Then it adds an unusually high reading and recalculates the average to show how an outlier can raise the mean. The main point is that even one extreme value can noticeably skew an otherwise valid dataset. Range and spread. In chemical engineering, averages such as temperature or pressure show whether a process is near its target, but the spread shows whether it is stable. 2 reactors can have the same average temperature, yet the one with larger fluctuations is less predictable and may carry more risk. A narrow spread suggests consistent operation, while a wide spread can point to measurement errors or process disturbances. The range shows spread by comparing the smallest and largest measurements, making it useful for seeing the full operating span and checking safety limits. However, unusual readings from issues such as faulty sensors or contaminated samples can distort it. Engineers often use standard deviation as well, because it shows typical variation around the mean. A small standard deviation suggests stable performance, while a larger one may point to problems such as formulation or temperature control issues. Understanding data spread helps engineers judge quality, safety, and process reliability beyond just the average. Even when average values look acceptable, High variability can reveal possible limit violations, unstable equipment, measurement issues, or sensitivity to changing inputs. Because some natural fluctuation is normal, engineers must interpret spread in the context of the physical system and measurement precision. Combining averages with variability leads to more reliable conclusions. Python code, range and spread. Range gives the full span of measurements, while spread describes the usual variation in a process. Engineers compare both to judge how the process is behaving before making decisions. We import the statistics module to use built-in tools for common statistical calculations. This makes it easy to compute key measures such as the mean and standard deviation for analyzing the script's data. We store the reactor outlet temperature readings in degrees Celsius as a list of decimal values. Keeping the data together this way makes it easy to analyze key statistics such as the average, range, and standard deviation, which help describe the reactor's behavior and operating stability. The code first checks that there are at least 2 temperature measurements, since calculating spread, such as standard deviation, needs more than one data point. If the list is too short, it raises an error explaining that at least 2 measurements are required. This prevents the program from making unreliable calculations with insufficient data. To understand temperature variability, find the lowest and highest recorded values using the minimum and maximum functions. Then, subtract the lowest temperature from the highest to get the range, which shows the total spread of the measurements. To summarize the temperature data, calculate the mean to find the average temperature. Then calculate the standard deviation to see how much the temperatures typically vary from that average, which helps show how consistent the process is. To find how many temperatures are unusual, first set a lower and upper limit by moving one standard deviation below and above the mean. Then check each temperature to see whether it falls outside that range. Counting those cases gives the total number of measurements more than one standard deviation from the mean. The analysis summarizes the temperature dataset by reporting how many measurements were included, along with the lowest and highest recorded values. It then gives the overall range and mean temperature to describe the spread and central tendency. Finally, it reports the sample standard deviation and counts how many measurements fall more than one standard deviation from the mean, identifying values that differ noticeably from typical temperatures. The code uses a 2-degree range as a simple threshold for judging temperature stability. If the data range is 2 degrees or less, it treats the spread as narrow and the system as likely stable. If the range is larger, it flags a wider spread that may indicate disturbances needing investigation. The code displays a concise engineering conclusion based on the calculated temperature range. It tells the user whether the spread is narrow, suggesting stable operation, or wide, suggesting possible disturbances that may need investigation. A formatted message keeps the output clear and easy to read. This script summarizes reactor outlet temperature data to judge how much the readings vary. After confirming there are enough measurements, it calculates the range, mean, and standard deviation, and counts readings more than one standard deviation from the mean. It then reports the key statistics and interprets the result. A range of 2 degrees Celsius or less suggests stable operation, while a larger range may indicate disturbances that need investigation. Data distribution. Data distribution describes how values are spread across a dataset. which is essential in chemical engineering because averages alone can hide important behavior. Two reactors may have the same average temperature, yet one may be stable while the other fluctuates widely. Looking at the distribution shows whether measurements cluster near a target, vary too much, or include outliers that need investigation. For example, unusually high viscosity readings may signal problems such as incomplete mixing or temperature variation. A distribution shows how measurements are spread, often by ordering them or grouping them into ranges. Many datasets are balanced, with most values near the center and fewer at the extremes, while others are skewed by process effects, such as concentration changes or unusually large particles. Distributions also reveal outliers, which engineers must judge carefully because they may be errors, equipment problems, or valuable clues about the process. Understanding data distribution helps engineers connect summary statistics to real process behavior. When data are tightly grouped and symmetric, the average can describe typical performance well. But when data are spread out, skewed, or clustered, the average may hide important patterns. In cases like startup versus steady operation, or a heat exchanger with occasional high temperatures, engineers need deeper analysis to identify consistency, safety, or efficiency concerns. Python code, data distribution. This section explores how process measurements are distributed using small synthetic reactor data. It compares normal steady operation with upset behavior to highlight how measurement patterns change under different process conditions. We import tools for generating, analyzing, and visualizing data. The random module helps create synthetic data with realistic variation. The statistics module supports measures like the mean and standard deviation, and pyplot from matplotlib lets us plot temperature distributions for easier comparison and interpretation. The random seed is set to 42, so the generated values are repeatable each time the code runs. Two temperature datasets are then simulated for comparison, 40 steady readings and 35 upset readings, both drawn from a Gaussian distribution with a mean of 85 and a standard deviation of 1.2. The data is expanded by adding a few higher temperatures to represent occasional process upsets. Then the steady and upset temperature lists are checked by comparing their lengths. An assertion confirms that both lists contain at least 10 entries, giving enough data points for meaningful analysis. The summarize function takes a label and a set of temperature values, then reports key statistics for the data. It calculates the mean and median to describe central tendency, the standard deviation to show variation around the mean, and the range to show the overall spread. Together, these measures give a compact view of the reactor temperature distribution. The code summarizes temperature data for engineering analysis by printing a label and 4 key statistics: the mean, median, standard deviation, and range. Each value is rounded to 2 decimal places for readability. It also returns these statistics so they can be used in later analysis or comparisons. The code uses a summary function to analyze temperature data for a steady reactor and a reactor with upsets. For each case, it reports key statistics such as the average, median, standard deviation, and range. These results make it easier to compare the 2 temperature distributions. The code explains that temperature distributions with similar averages can still have very different shapes. This shows why the mean alone may not be enough to judge process stability. A wider spread and a high tail can signal possible instability, so engineers should examine the full distribution, not just the average. Create a clear comparison plot by overlaying 2 histograms, one for steady temperatures and one for temperatures with upsets. Use the same number of bins and transparency for both, so their distributions can be compared directly, making differences in spread and shape easier to see. The plot is made easier to interpret by labeling the horizontal axis as outlet temperature in degrees Celsius and the vertical axis as the number of readings. A clear title identifies it as the distribution of reactor outlet temperatures, and a legend distinguishes the datasets, such as steady and upset conditions. The tight layout function adjusts the plot so labels, titles, and other elements fit cleanly without overlapping. The show function then displays the plot window, allowing the user to visually inspect the distribution of reactor outlet temperatures and compare it with the earlier numerical summaries. This script compares simulated reactor temperatures during steady operation and upset conditions. It generates both datasets, summarizes them with measures such as the mean, median, standard deviation, and range, and shows that similar averages can hide very different behavior. Histograms reveal that upset conditions produce a wider spread and a higher temperature tail, suggesting greater variability and possible instability. Engineering data interpretation. Contextual conclusions. Contextual conclusions turn raw numbers into useful engineering insight. Values like average temperature or maximum pressure only matter when interpreted against the material, equipment, control limits, and process behavior. A temperature rise or pressure variation may be safe in one system, but risky in another, especially in sensitive processes. Effective data interpretation connects measurements to performance, safety, and efficiency. A strong engineering conclusion connects a statistic to what it means for process performance. An average value near a specification or regulatory limit is not enough by itself, because high variability or extreme values can still create off-spec products or compliance problems. Good decisions must consider the mean, the spread, the extremes, and how they relate to important thresholds, so the process can be judged for real robustness rather than average performance alone. Context is essential when interpreting data, especially when datasets are small or incomplete. Measurements from stable conditions may not represent startup, seasonal, or other changing conditions, so apparent issues like falling heat exchanger temperature or high compressor vibration need process knowledge before drawing conclusions. Good analysis uses statistics as evidence, but avoids overconfidence and supports the right follow-up actions or investigations. Python code, contextual conclusions. Safety summaries should connect statistical results to practical engineering decisions. Numbers alone cannot prove that a system is safe, so thresholds are needed to show when the evidence calls for action. The script imports Python's built-in statistics module to analyze reactor temperature data. This module provides tools such as mean and standard deviation, which helps summarize system performance. It is given a shorter name so its functions are easier to call and the code stays cleaner. A list of reactor temperature readings in degrees Celsius is stored for later analysis. These measurements will be used to calculate statistics and evaluate the reactor's operating status. The reactor uses two temperature thresholds to judge operating conditions. The normal target is 80 degrees Celsius, which represents ideal operation, while the caution limit is 83 degrees Celsius, signaling that the temperature may need attention. Together, these limits help determine whether the reactor is running safely or if further investigation is needed. We summarize the temperature data by calculating its average, measuring how much the readings vary with standard deviation, and identifying the highest recorded temperature. To count temperature readings above the caution limit, Check each reading and count how many are higher than the limit. Then find the total number of readings, which lets you compare the high readings to the full set and understand their proportion. The logic evaluates temperature data to decide the reactor's status. If the average temperature stays within the caution limit and no individual readings exceeded, the reactor is considered stable and operating near expected conditions. If any readings exceed the limit, the average may still be acceptable, but those excursions need further investigation. The output summarizes reactor temperature behavior by reporting the average, standard deviation, and maximum temperature, each to 1 decimal place in Celsius. It also shows how many readings exceeded the caution limit compared with the total number of readings. Finally, it presents a short conclusion that interprets these statistics to assess the reactor's temperature stability and operational status. The script checks reactor temperature stability by calculating the average, standard deviation, maximum temperature, and how many readings exceed a caution limit. It then compares the results with that limit to judge performance. If the average is below the limit and no readings exceed it, the reactor is considered stable. Otherwise, the average may still be acceptable, but any temperature excursions should be investigated. Trends. In chemical engineering, trend analysis helps engineers understand how a process behaves over time, not just at single measurement points. Tracking values such as temperature or pressure can reveal whether a system is drifting, stabilizing, or losing efficiency. For example, a steady drop in heat exchanger temperature under constant steam flow may suggest fouling or an instrumentation problem. Interpreting trends means connecting data patterns to the physical and chemical processes behind them. Changes such as rising pump pressure or falling product purity may signal equipment, material, or performance issues. But trends are evidence, not final conclusions. They should be judged in context, including factors like feed changes or maintenance, using data summaries and engineering judgment to decide whether they affect quality or safety. Be careful when interpreting trends because short patterns can come from random noise rather than real change. A trend is more credible when it is consistent and supported by related measurements, such as yield changes matching process control data or wastewater demand matching production changes. State conclusions with cautious language and recommend practical follow-up, such as more sampling or equipment checks. Python code. Trends. Trends help turn measurements into meaningful stories about an engineering process. Even small datasets can show slow process drift, while summary statistics support careful, evidence-based conclusions. We begin by importing key Python libraries for working with text data. The CSV module handles dataset files. The I/O module treats strings like file streams, and the statistics module supports basic numerical analysis such as averages and variance. Together, these tools prepare us to process and analyze the dataset. A small process dataset is stored as a multi-line string so it can be read easily later. Each row records a day number, outlet temperature in degrees Celsius, and steam flow rate in kilograms per hour, making the data ready for CSV-based processing. The code reads a text-based dataset using the CSV module's dictionary reader, treating the text like a file through a string input object. Each row becomes a dictionary with column headers as keys and row values as data. The reader is then converted into a list of dictionaries, making the dataset easier to access and analyze. Before doing any calculations, the code checks that the dataset has at least 2 rows. This matters because statistical analysis needs more than one data point to be meaningful. If there are too few measurements, it raises an error, so the later results are not invalid or misleading. The code prepares text-based dataset values for analysis by converting them into numbers. It turns the day entries into integers and converts outlet temperature and steam flow entries into floating point values. This creates numeric lists that can be used for statistical calculations and trend analysis. We summarize the dataset by calculating the average outlet temperature and the average steam flow using the statistics library. We also measure temperature variation by finding the difference between the highest and lowest outlet temperatures. Finally, we compare the first and last temperature readings to show the overall temperature shift over time. To estimate the temperature trend, find the number of days between the first and last measurements, then divide the total temperature change by that time span. The result is the average temperature change per day, showing whether temperatures are generally rising, falling, or staying stable over time. The code uses the temperature trend slope to decide how to describe the data. If the slope is below -0.2, it reports a meaningful decrease in temperature. Otherwise, it treats the temperature as roughly stable. The output summarizes key process indicators: average outlet temperature in Celsius, the temperature range, the daily temperature trend, and average steam flow in kilograms per hour. It then interprets whether the temperature behavior is stable or trending downward. If steam flow remains stable, the analysis recommends checking for possible fouling or instrumentation problems. This script analyzes daily outlet temperature and steam flow data to detect process drift. It reports the average and range of the outlet temperature, the average steam flow, and the temperature trend over time. If the temperature is clearly decreasing while steam flow remains stable, it recommends checking for fouling or instrumentation problems. Quality conclusions. In chemical engineering, good conclusions depend on more than average values. Data summaries help show whether a process or product is reliable, stable, and safe enough for action. For example, reactor temperatures may have an acceptable average, but large variation or readings near safety limits can signal control problems. Reliable decisions must consider both typical performance and variability, because a process that fluctuates too much can create safety risks and inefficiencies. Engineers should interpret data summaries by comparing statistics with what the system is expected to do. Averages, ranges, and standard deviations can show whether a process appears stable and reliable, but no single number is enough. High purity with low variation suggests good separation, while low readings or rising pressure drop can reveal inconsistency or fouling. Sound quality judgments come from the full data pattern, not just the most favorable statistics. Strong engineering conclusions depend on understanding uncertainty, limitations, and whether more data is needed. Data summaries should be judged in context, including sample size, measurement precision, and possible process issues. The goal is to connect statistics to engineering meaning, showing whether the evidence supports confidence or raises concern for decision-making. Python code. Quality conclusions. Use statistical summaries to support engineering quality decisions. Built-in tools can analyze small process datasets, turning statistics into clear evidence for action. We import 3 modules to support data handling and analysis. The CSV module helps read and write structured text data. The input and output module lets us treat strings like file streams, and the statistics module, called stats here, provides tools for calculating measures such as the mean and standard deviation. A small dataset of purity percentages is stored as a multi-line text string. It contains 6 runs, with each run paired with a purity value, and begins with a header naming the 2 columns. Because the format resembles a CSV file, the data can be parsed easily with CSV tools later. The CSV dictionary reader loads the purity data, so each row is treated as a dictionary using the column headers as keys. The purity percentages are then extracted and converted from text into floating point numbers. This turns the raw CSV text into a usable list of numeric purity values for later calculations. Set the purity specification limit at 98.5% to judge product quality. Then summarize the purity data by finding its average, minimum, and maximum values. Together, these measures show the product's overall purity level and how much the results vary. The code summarizes purity performance by measuring the spread of the values using both the range and the standard deviation. It also counts how many purity results fall below the specification limit, showing how many runs fail to meet the required quality standard. The quality decision is based on run failures, variation, and average purity. If there are no failed runs and the sample standard deviation is at most 0.3, purity is considered stable and above specification, so it is accepted. If the average meets the specification but some runs fail, the result is concerning because individual runs fall short. Otherwise, the product quality is rejected as inadequate. The output summarizes solvent purity quality by reporting the average purity, the minimum to maximum range, and variability using the range and standard deviation. It also counts how many runs fall below the required purity limit to highlight possible quality concerns. The final printed conclusion gives an overall judgment on whether the product quality is acceptable, concerning, or inadequate. This script evaluates solvent purity data for quality control by calculating summary statistics, such as the average, range, and standard deviation. It counts how many runs fall below the 98.5% purity limit, then uses these results to decide whether the product is stable, concerning, or unacceptable. Finally, it prints a concise summary of the key measurements and the quality decision. In this lecture, you learned to import simple process datasets from text files using built-in Python tools, compute descriptive statistics for chemical engineering measurements, and interpret data summaries to support engineering conclusions. Congratulations on completing this course. Thank you for your attention. See you all in the next lecture.